All right, okay. The wave chapter that you've learned before this was more about the introductory part to waves. And most of the time you were only dealing with one wave. You were only thinking about one wave and analyzing one particular wave. But in a lot of cases, you normally do not have only one wave. You have actually two or more waves in practice. So what we're interested to know is what happens when one wave meets another wave, okay? That is what superposition is. The chapter of superposition will be more on the study of what happens when different waves meet each other. The previous chapter on waves itself, you did not really bother about that. You were only considering the waves individually. In this new chapter, superposition, you will consider what happens when waves, more than one wave, meet each other. All right. So to start it off, what is principle of superposition? Okay. When we have waves that travel and overlap, a new wave is temporarily formed, which can be explained by principle of superposition, which states that at a point where two or more waves meet, the resultant displacement is the sum of individual displacement due to each wave at that point. So if you have one wave, wave A, and one wave, wave B, they meet together at one point, they will form a new wave, C. Okay, the new wave C will have its displacement, its resultant displacement as the sum of displacement of all the waves before it. Okay, so the resultant displacement is obtained by plotting the sum of the two waveforms when the two waves are present simultaneously at the same place. Okay, principle of superposition can only be applied to waves, and when you want to apply to waves, the waves must be of the same type. So previously when we talk about waves, remember there are actually two kinds of waves. One is transverse wave, and then another one is longitudinal wave. So when you want to apply principle of superposition to waves that meet each other, they must in the first place be of the same type. So for example, if I talk to you about a light wave meets a sound wave, they do not form a new wave because you see light wave is transverse, sound wave is longitudinal. So although those two waves can meet together at one particular point at the same time, they do not form a new wave. They do not superpose with each other. They do not form a new wave because they are in the first place different types. One is transverse, one is longitudinal. But if you have the same type, then they can be combined together. Let's just say light and a beam of X-ray. Light, as I mentioned to you, is transverse wave, and then X-ray, since you know that X-ray is EM radiation, is also transverse wave. So in your case here, if both are transverse wave, light and X-ray, these two can combine together to form a new wave. Okay, so just bear this in mind. Superposition applies to waves, but when you're talking about waves, it must be the same type of wave, either transverse, or longitudinal. It cannot be mix and match. All right. Okay, so principle of superposition is actually used to explain many wave phenomena, such as interference, diffraction, stationary waves, or even beats in sound. Okay, this will be the later part. Okay, now, just like I mentioned to you that when waves meet, they will combine together to form a new wave. This diagram here basically shows you that. So if, as I say, I have wave A, which is this one, and then I have wave B, which is this one, they will combine together to give me a new wave, which is this one. Okay. The displacement of the new wave is actually the sum of the displacement of the individual waves. What do I mean by that is that I can give you some example here, just a simple illustration. If let's just say I tell you that this one is, say, 0.5A, and then this one here, I tell you is A. So when these waves combine together, at this particular point that I'm interested in, the displacement of the new wave is actually the sum of the displacement of the individual waves. If at this point, wave A had 0.5 A, wave B is just A, the new wave C or wave A and B, the resultant wave, it will be 1.5 A because it came from 0.5 A plus with 1 A giving you 1.5 A. So this is what we meant by that statement actually. At a point where two or more waves meet, the resultant displacement is the sum of the individual displacement of the wave at that point. So at this little point here, the green dotted line here that I've drawn, you have two waves. One with an amplitude of 0.5 A, one with an amplitude of A. The new resultant displacement would be the sum of these two displacements. So I add them out, 0.5 A plus 1 A giving me 1.5 A. So the same thing can also be said for some other point. Maybe let's just say I thought about this little point here. So here you see wave A has 0 amplitude. Wave B also has 0 amplitude. So if I want to add up the amplitudes together, sorry, not amplitude, 0 displacement. Wave A has 0 displacement, wave B has 0 displacement. If I want to find out the new displacement of the resultant wave, it's just 0 plus 0, giving me 0. That's why you see here has nothing. Okay. So that is the basic concept behind it. At any point, just add out their displacements together. That one will give you your new wave. All right. So another example would be like the ones below here. You just look at this one. If let's just say you have wave A, which is this one, and then wave B is this one here, your new resultant wave is going to be this one. So how you get this in the first place? Same concept here. This one, say for example, I tell you is maybe, how much I say this? This one, let's just say for example, I tell you is 1.5 A. Then this one, for example, is say maybe 3.5 A negative because it is below the x-axis. So what is the displacement of the resultant wave? At this point, let's just say I'm interested in this location here. Okay, so what is the new displacement of the resultant wave? This one will be 1.5 plus negative 3.5. Sorry, I forgot to put the A inside. This one will be 1.5 A plus with negative 3.5 A, giving you negative 2A. Okay, so this is another way where you can, this is actually how you add up the displacement together. When you add up the displacement together, please be mindful of whether it has a negative sign to it. You need to include the negative sign because when we say displacement is a vector, right? It has a direction associated with it. It would have positive and negative. So when you add them up, please make sure that you are taking into account the positive, negative inside. All right. So this is the first most basic understanding of superposition. You want to add, when you have two or more waves together, just add up their displacement to get the new wave. All right. Okay, now next one we talk about interference. Now superposition of wave is actually just known as interference. It's also commonly known as interference. So for interference or superposition to occur, there are actually three main conditions. They must first meet each other at a point. They must be same type of wave. And then the third one would be they must be polarized in the same direction. So this one was what we just learned in the previous chapter when we talk about transverse wave can actually oscillate in many different planes, many different directions. Once you polarize them, you're only causing them to oscillate in one plane, one direction. So in order for interference or superposition to occur, these are the 3 points you need, okay? They must first meet at a point. They must be same type, transverse, transverse, longitudinal, longitudinal, cannot mix and match. And then after that, they must be polarized also in the same direction, all right? Okay, then after that, another thing that we will tell you is that at the point where waves meet, the amplitude of your resultant wave depends not only on the amplitudes of the individual waves, but also on their phase relationship. This is where your understanding of phase difference comes in, all right? Now, under IGCSE or SPM, you would have probably learned something about constructive interference and destructive interference. So we are going to revisit this in detail now for this chapter. When we talk about constructive interference is where you get a resultant wave of increased amplitude or intensity when waves meet in phase. Okay, so what we'll tell you here is that the amplitude or intensity is actually maximum. You get the maximum possible amplitude, you get the maximum possible intensity. Now, intensity and amplitude are both related to each other because you know that intensity is proportional to amplitude squared. So when we say amplitude, when we say intensity, they're actually one of the same thing because they're closely related. So constructive interference will tend to give you a wave with increase in amplitude, increase intensity as a result of the waves meeting in phase. Okay, so when we say they meet in phase, that means the phase difference here is 0 degrees. In other words, crests and troughs coincide. So the easy way to look at it will be the diagram on your right. Let's just say you have two waves for constructive interference. This is wave number 1, and this is wave number 2. Okay, so when they meet under constructive interference, crests will tend to meet with crests. Trough will tend to meet with trough. In other words, the peak will meet with the peak. The peak will meet with the peak. The valley will meet with the valley. Okay, crest coincide with crest. Trough coincide with trough. This is what constructive interference actually is. This one is crest. Then this one here is your trough. Okay, constructive interference is where your waves always meet in phase. Crest meets crest, trough meets trough. It will result in a wave of increased amplitude or intensity. Generally speaking, your intensity and amplitude will be maximum. This will be the maximum possible it will ever go. Nothing will go higher than that. All right. So then after that, the opposite will be destructive interference. Okay. Now, destructive interference produces a resultant wave of reduced amplitude or intensity when the waves meet out of phase. Here, when we say meet out of phase, the phase difference is actually 180 degrees out of phase. When you have a phase difference of 180 degrees, it means a crest meets with a trough. Okay. So remember just now I mentioned to you, when you want to add up the displacements of the individual waves to get your resultant wave, you always need to take into account whether they have negative. So in the case where a crest meets with a trough, usually what happens is that a crest has a positive value of displacement, whereas a trough has a negative value of displacement. So it won't be difficult to see that if you have a positive value add with a negative value, you tend to get something that is much less. All right. So here we tell you a crest coincides with a trough to give you a wave of reduced amplitude or reduced intensity. So generally speaking, destructive interference gives you amplitude or intensity that is minimum. Okay. it is the smallest possible that you will ever get. Nothing will get lower than that. Okay, amplitude intensity is minimum. So an example you can see here is the diagram on the right. Again, you have those waves. You have wave 1 and wave 2. So when they meet out of phase, the phase difference is 180 degrees. Crest will meet with a trough. So you look at this diagram here. You will see that this one is crest, this one is trough. And then you look at this one and this one is actually the trough, this one is actually the crest. So here, assuming that they are the same value, you're gonna get complete cancellation, you get nothing, right? I can give you some values here. If this one is say A, this one is negative A plus negative A obviously will give you 0. Or if this one is negative A, and then this one is A, you will still get 0, okay? Now, if you look at the constructive interference part, crest means with crest, trough means with trough, you will get a new wave that is larger than before. It has increased amplitude, it has increased intensity. So if you want some values to appreciate it, you can also say that this one has, say, amplitude A, this one negative A, this one negative A. So A plus A will give you 2A. Negative A plus negative A will give you negative 2A, right? So whereas this one here will always give you 0, okay? So this one here, let me just make sure that I mention this to you. Provided the amplitudes of both waves were equal, right? Meaning to say if this is A, this one also has same magnitude, negative A. Only then can you have complete cancellation, all right? Yeah, actually I mentioned this already in the bottom part here. If the waves are of the same amplitude, let me just clear off everything. If the waves are of the same amplitude, resulting amplitude will be twice the individual amplitude for constructive interference. Yeah, I actually just put the values there already just now for you. So A gives you 2A. This is for constructive interference. Okay. If you are talking about destructive interference, you have A and then negative A, you're gonna get 0. All right, that one is explained under this statement here. All right. Now this one is assuming that they have same amplitude in the first place. All right. Now, what happens when your waves do not have same amplitude? If the waves do not have equal amplitudes, the most important thing you need to know from this is that destructive interference will not result in complete cancellation of the waves. Okay, so a common thing that most people misunderstood is destructive wave always gives you 0. That is not true. Destructive interference always gives you minimum amplitude or minimum intensity, which could happen to be 0. Okay, what makes a destructive interference destructive is the way they meet. Okay, as long as you see, as long as the phase difference is equals to 180 degrees, where the waves meet out of phase, this is destructive interference. Okay, what defines interference to be destructive is how they meet, is the phase relationship. If you see that the phase difference is 180, the waves meet out of phase, this is confirmed to be destructive interference. Okay, so the resulting amplitude may or may not be 0. Okay, so just because you see something, the amplitude is not 0, doesn't mean that it cannot be destructive interference. It can also still be destructive interference. Okay, so what I just want to say is just this: if you want to see whether something is destructive interference, just look at their phase difference, how they meet. If their phase difference is 180 degrees, they meet out of phase, mean to say crest meets trough, this is always destructive interference. Okay, the resulting amplitude may or may not be 0. Okay, so if your waves do not have equal amplitudes, destructive interference will not result in complete cancellation of the waves. Okay, so just because you don't have complete cancellation doesn't mean that it cannot be destructive. It is still considered to be destructive because crest is still meeting trough. Phase difference is still 180. Okay, so when we say you do not have complete cancellation of waves, it is something like this. Actually, this one will be under some other page. Yeah, if you look at page 5, okay, I'm just going to skip a little. Under page 5, because I want to explain the part where you're talking about destructive interference. Okay, look at page 5. Near the diagram with the waves at the bottom of the page, if waves are not, if the amplitudes are not equal, complete cancellation of waves do not occur during destructive interference, because a small amplitude trough cannot completely cancel a large amplitude crest. So what we mean by that is something like this. You see, I have two waves here. I have the blue colored wave, and then I have the orange colored wave. Notice that this one is meeting out of phase, or in other words, crest is meeting a trough. So by definition, this is destructive interference because they are meeting 180 degrees out of phase. All right, but the amplitudes are not the same here. So this one here could be having an amplitude of, say, maybe A. This one could be maybe having an amplitude of maybe negative 0.8 A. So if I want to find out the new resultant displacement for the new wave shown on the right, this one would be 0, this one would be A plus with negative 0.8 A, giving me 0.2 A. Okay, so that one is actually this point here. Okay, shown here. All right, so this is still considered to be destructive interference. The amplitude, the resulting amplitude is not 0. It does not mean that it's not destructive. It is still destructive. Okay, because what really defines something as destructive is crest meets trough, or phase difference is 180 degrees. All right, so this is something that some people always tend to get confused with. All right, just because something is not 0 doesn't mean, so just because something is not 0 doesn't mean that it's not destructive. It can be destructive. All right, so back to the second page here, where I mentioned that if the waves do not have equal amplitudes, destructive interference would not result in complete cancellation of the waves. You can actually maybe write a small footnote here, refer to page 5. You can actually refer to that. Okay, so for other phase differences, neither in phase or neither out of phase, resulting amplitudes will be somewhere between the two extremes, either between a maximum or between a minimum. So just now I told you that constructive interference always results in maximum amplitude intensity. Destructive interference always results in minimum amplitude or intensity. Okay, so if you have something where the waves meet with phase difference that is between in phase or out of phase, your amplitude will be in between the two extremes. Okay, where the waves meet off. Okay, so that part is all right. Okay, then after that, I talk to you about diffraction. Okay, so just bear with me for a while. Okay, now let me go on to something else called diffraction. Diffraction is where your wave spreads out when the wave is incident on the slip or the edge of an obstacle. Now, when we talk about a slit or aperture, it's actually just a gap. It's actually a gap, all right, where a wave is incident on. Okay, so what we'll tell you is that when a wave passes through a small opening or is blocked by an object, it will spread into regions where shadows are expected. All right. So the amount of diffraction depends on the relative size of the opening and the wavelength. So what we'll tell you is that when the size of the opening is comparable to the wavelength, significant diffraction occurs. So what do we actually mean by that? You will have to see the diagram below. Say, for example, you look at the first set of the diagram. You have waves that are indicated by these blue colored lines here. All right. These are your waves. All right. Then after that, the waves is passing through some sort of gap. All right. So your gap, the size of your gap can be different. The size of your gap could be something like this, or it could be something like this. Okay, this is your gap size. All right. So when we say that a wave spreads once it passes through an aperture, a slit, or a gap, it is referring to something like this. Okay. So this one here, the diagram on the left shows you small diffraction. You notice that when this wave passes through the gap, it actually didn't bend much. It actually didn't spread out much. When we say spread, it's something like this. Spread, okay? Because the definition of diffraction is spreading of a wave when wave is incident on a slit. So you notice that when the wave passes through this gap, the wave actually didn't spread much. But then on the other hand, when you have a smaller gap in the second diagram, you notice that the wave actually spread out quite a bit. Okay, you can actually see the wave spreading. Okay, so this one here is what we call as significant diffraction. The earlier diagram is actually small diffraction. Okay, so the relative size of your gap with the wavelength affects the amount of diffraction that you get. All right, so when the size of the opening, the slit width is equal to or slightly smaller than the wavelength, the wave will diffract significantly. So sometimes they may give you some little diagram and then ask you to see from that diagram whether some significant diffraction is going to occur or not. So you have to make use of this information here. You have to compare the size of the opening and compare with the wavelength. All right. Now, how you want to see the wavelength is you see the distance between the lines here. Okay, you see this blue lines here is actually your wavefront. Okay, this little blue lines here is actually your wavefront, or in other words, your wave crest. So if you're talking about distance from one wavefront to another wavefront, it's actually the same as distance from one wave crest to another wave crest. Okay, one wave crest to another wave crest. So this one is lambda. Okay, so each blue line here represents a wavefront or wave crest. Distance between adjacent wavefronts or adjacent wave crest is equals to lambda. So when you want to evaluate by just looking at the diagram whether significant diffraction will occur, you actually just look at the gap between the wavefronts and the gap of the slit itself. If they are comparable, significant diffraction will occur. If you notice that they are not comparable, like the first diagram, this one is the wavelength, this one is the gap. You see, they are not comparable. One is so much bigger than the other. So this one will not have significant diffraction. Okay, so when you want to evaluate the diffraction, you can either look at the diagram or you can actually do something to calculate out the amount of diffraction. So in general, what we'll tell you is that if you want to calculate out whether something is going to have a lot of diffraction, you just think of it as this. When wavelength lambda is incident on a slit of width W, the bigger the ratio of wavelength to wave, the bigger the diffraction. Meaning to say you get the ratio of lambda over W, the bigger your ratio that you get, the bigger the amount of diffraction you will have. Okay, so that is for diffraction. Now, the ones that you see here is only for waves passing through a gap. You could also have diffraction for waves that are incident on the edge of an obstacle. It hits the edge of one obstacle. That one is shown by the second set of drawing. The edge of the obstacle is actually this thing here. Okay, the waves that you have is actually this one here. All right. So when your waves are incident on the edge of an obstacle, you will also have diffraction. So your diffraction is actually shown by these arrows here. You see your wave spreading. Okay. So this one you see when you compare the left diagram versus the right diagram, this one seems to be spreading less compared to this. All right. So why does the second diagram here spread out more than the first one is because you see the wavelength here tends to be comparable to the size of the opening. Oh, this one cannot use, right? What would I compare it with? This one doesn't have any gap size to compare it with. The edge of the obstacle could be something very long like this. There's nothing I can compare with. This one is a very bad example to use. Okay, don't bother about this one. Just know that when we're talking about diffraction, you just look at the amount of spreading. Does it spread out far? If it spreads out far, it is significant diffraction. If it doesn't spread out far, that isn't significant diffraction. To evaluate whether the diffraction is going to be more or less, you have to look at the size of the gap, size of the opening with the wavelength. If you're talking about edge of obstacles, you can see the wavelength, but you cannot see the size to compare with for the edge of the obstacle. So this one not applicable for edge of obstacle. So don't bother about that. Okay. So that one is for diffraction. Then after that, there could also be something on coherence. Okay, maybe I better not do coherence. Maybe I just do one or two short questions for you. Maybe I just give you the example of lambda over W. Okay, just have a look at your worksheet. I just give you one small example of what I meant by using that little equation. Okay, just open your superposition worksheet. If you want to look at some examples on diffraction, that one will be under page 10. Okay, just look at page 10. Okay, page 10 of your worksheet. I can't do much example today, but I can give you some. Just look at page 10 under question 28. Okay, page 10, question 28. Question 28. Now, water waves of wavelength lambda are diffracted as they pass through a gap of width d in a barrier. Which combination of wavelength and gap width will produce the greatest angle of diffraction, or rather the greatest amount of diffraction? So just now, as I mentioned to you, when you want to see whether you're going to have significant diffraction or not, you can either always look at the diagram to see whether you're going to have significant diffraction. In this case, you compare the wavelength size with the gap size. But if let's say they don't give you a diagram, you have to use an equation to calculate, which is this one. So this question is one of those questions. They don't give you a diagram, so you can't do any comparison. You instead need to do something like a calculation. So which combination of wavelength and gap width will produce the greatest angle of diffraction? So you just get the ratio of the wavelength to the gap width. Okay. So in your case, lambda over d. In the notes, I wrote it as lambda over w. But here the width is actually written as d. So I just use the same symbol. So what you do is you take the ratio of lambda over d See which one gives you the largest value. All right, so in your case, 2 divided by 0.5 will give you 4. Then this 1.5 divided by 0.5 will give you 1. 2 divided by 2 will give you 1. Then 0.5 divided by 2 will give you 0.5. So you see, if you take the ratio of the wavelength to the gap width, these are the corresponding values of the ratio. So you'll notice that one of it is actually very much larger than the other. So this one will have the greatest diffraction. Okay, so the answer is A. In this chapter, that time I mentioned that we were talking about what happens when two waves meet each other. So I mentioned that when we have two waves meeting each other, they will form a new resultant wave, which can be explained by principle of superposition, where we say that the resultant displacement of the new wave is the sum of the individual displacements due to each wave at that point. So that time I mentioned to you that let's just say that you have 3 different diagrams here. Each of this diagram contains 2 different waves. So those 2 different waves meet together at one point, which in turn results in a new wave. So an easy example would be this diagram here, where we say that we have wave A and then we have wave B. So when they meet, they will form a new wave. That is this wave. Okay. So the other examples here are actually just the same thing, where we say that the resultant displacement is the sum of the displacement of the individual wave. The other day we also mentioned something about interference, well, which is actually another name for superposition. That time I mentioned to you that there are 2 very specific cases of interference that you need to know. The first one is constructive interference. The second one is destructive interference. Constructive interference is when the waves always meet in phase. It will cause a resultant wave of increased amplitude or intensity, whereas destructive interference is when waves meet out of phase. So it will result in a wave of reduced amplitude or intensity. Okay, so that's what I briefly mentioned in the last lesson. Okay, so now we talk about something similar again. If you look at page 4 of your notes, okay, page 4 of your notes, the one where we talk about 2 source interference patterns. Now, first thing first, you need to know what we call as coherence, right? Okay, Regan is here, right? Okay, hi Regan. So you just joined in. I was just recapping a little about what we mentioned, what we learned in the last lesson. So you just join in on time. Okay, right. Just look at page 4 of your notes which talks about 2 source interference. The first thing you need to know is what we call as coherence. Okay. So coherence is a question that they will always ask you. They will ask you to explain the term coherence. Coherence means waves have constant phase difference. Okay, this is the most important thing to know first. Whenever we ask you what is coherence between 2 waves, it means that the waves have constant phase difference. We learned how to calculate phase difference in the previous chapter, so by now you should be able to know a little how to calculate it out. All right. Now, coherence means that the waves have constant phase difference. They can have different amplitudes. It doesn't matter. All right. Now, constant phase difference will also imply that the waves have the same period, the same frequency, the same speed, and the same wavelength. Okay, this one I'll explain a little bit more later. But let's just single out the first statement first when we say that waves have constant phase difference. If you look at the examples on the screen right now, you should have 4 different diagrams. Okay, the first diagram is this one, second one is this one, third one is this one, and then the fourth one is this one. Okay, so for all 4 of these diagrams, this is coherence. Okay, you see that there are two different waves here, the dotted blue wave and the red colored solid wave. All right, these two waves are all considered to be coherent because there is constant phase difference. All right, so let's just say if I look at the first example, you can see that the phase difference here is actually 0. Remember that in the previous chapter, when we wanted to find phase difference between two waves, we mentioned that we will always pick 2 points that are similar. It could either be the crest and crest, or trough and trough, or even the equilibrium position. So right now, no matter which pair of points that we pick that are similar to each other, this one or this one or this one, we see that there's no difference between those 2 points. So the phase difference is 0. If you look at the second diagram, we again have the 2 waves, the red wave and the blue wave. So right now we want to find out the phase difference between those two. I can pick the crest of the red colored wave and also the crest of the blue colored wave. So right now you see this one here will be representing my phase difference. So when you compare this with respect to one full cycle, which is this one, you can see that this is actually half a cycle, which when changed to angle degrees is multiplied with 360, giving you 180 degrees. So this one is the first set of points that I can choose to compare. What if I choose the trough position? Maybe I choose the trough position on the red colored wave as well as the trough position on the blue colored wave. Maybe I choose it at here. Okay, maybe I choose here. So here, I will also still say that this is my phase difference. Okay, again, you see when compared with respect to one whole full cycle, it's actually half a cycle, which is actually half of 360, giving you 180 degrees. Okay, so no matter which pair of points that I pick, I will always get the same phase difference. You see, if I pick this set, I'm getting 180. If I pick this set, I'm also getting 180. If I pick the equilibrium position going downwards, let's just say for the red wave, this one, and the blue wave is this one, again, you see my phase difference is going to be the same. Okay, here my phase difference is again still half a cycle, half of 360, giving you 180 degrees. Okay, so you see, no matter which pair of points that I pick, I am always having constant phase difference. This is what coherence means. So if you repeat this analysis for the third diagram or for the fourth diagram, you will still get that conclusion that the phase difference is always going to be the same. Okay, so now even though the amplitudes could be different, like in the third example here, you see the red colored wave had an amplitude up to here. For the blue colored wave, it had an amplitude up to here. The amplitudes being different actually have no effect on your phase difference. Okay, this one I mentioned it to you before last time. So here, similarly, you having different amplitudes has nothing to do with coherence. Coherence is just strictly speaking phase difference. Okay, so for the third example, phase difference is 90 degrees. For the fourth example, phase difference is also 90 degrees. Okay, no matter which pair of points I pick, I will always have constant phase difference. And then you see here, there's one thing you should be able to notice. In order to have constant phase difference, the waves must have same frequency or period. Okay, frequency and period are interrelated because f is equals to 1 over t. Okay, so you see right now, notice that for all 4 examples here, this one, and this one, If you look at the period of the waves itself, you will see that they're actually all the same. See, for this one, the period T for the red colored wave and blue colored wave is the same. For the second diagram, it's actually also the same. They have the same period. Okay, so this one here for the third diagram, this one is the T. This one is also the T. Okay, wait, sorry. This one is not the correct diagram. For the third diagram, yeah, you still get in the same period T, all right? Because you see this one is T. This one is also T, okay? So you see they all have the same period. Needless to say, the fourth diagram is also going to be the same. They're also going to be having the same period, okay? So if you have same period, you're going to have same frequency also, because as I mentioned to you, frequency is equal to 1 over T. So here you see when those examples here have constant phase difference, are coherent, the only way they can be coherent is when they have the same period and hence frequency. Okay, so that's why here I mentioned to you, constant phase difference already implies the waves must have same period and same frequency. Okay, so the moment you see something mentioned to you as being coherent, you should automatically relate it to the waves having same frequency and period, because that's the only way you can have same, that's the only way you can have constant phase difference. So what if you do not have the same period, you do not have the same frequency? So if you do not have the same period or same frequency for the waves, you're not going to have coherence. If you look at the diagram below here, the fifth diagram, let me clear off whatever I have here. If you look at the last diagram, the fifth diagram here, you again have two different waves, but you see here the waves are clearly not having the same period or frequency. You have wave R that looks like this, and then you have wave S that looks like this. Okay, so you can see that clearly they do not have the same period. This one for wave S, this is the period, and then for wave R, this is the period. So you see they have different periods, so obviously they're going to have different frequency. So if they have different period and frequency now, they are not going to be coherent. They're not going to have constant phase difference. So why do I say that? You can look at the next page. The diagram that you see on the next page, on page 5, is actually a blowout of this same diagram. All right. So here, let's try to find out what is the phase difference by picking a set of points. All right. So right now, remember that when we're talking about phase difference, finding phase difference between 2 points, we always need to find points that are similar to each other. If you pick crest, you must pick crest. If you pick the trough, you must pick the trough. If you pick the equilibrium going down, you must pick the equilibrium going down. If you pick the equilibrium going up, you must also pick the equilibrium going up on the other wave. So let's just say right now, we try to do the same here. Okay, we have the two waves, the red colored wave and the blue colored wave. Okay, so when it comes to finding phase difference, we always compare with respect to one cycle. In your previous chapter, I mentioned to you, phase difference is the fraction of a cycle where a wave leads or lags the other. Okay, fraction of a cycle that a wave, it's fraction of a cycle that a wave will lead or lags the other. The important thing is to know that phase difference is always fraction of a cycle. So right now, you see here, there are two different waves of two different periods. So which cycle do I want to compare with? Let's just say that I compare with the smaller wave instead. Let's say right now I compare the cycle as this. I compare with respect to this blue cycle, with respect to the smaller period. Wait, now let me just see this. What can I use? The cycle that I want to compare to is this one, okay? The pink one, all right? So right now, let's do our phase difference. I want to pick, say, the equilibrium going up and equilibrium going up for both waves. If I pick this point, here, my phase difference is 0. Okay, wait. Here you see my phase difference is 0. If I pick the equilibrium going up for both waves, my phase difference is 0. But if I pick the crest position for both waves, this one and this one, now this is my phase difference already. Now, if I compare with respect to one cycle, which is this pink colored cycle here, you will see that this is actually a quarter of a cycle. This phase difference here is a quarter of a cycle, is a quarter of 360, it's actually 90 degrees. Now, then if I repeat the analysis again for another set of points, say this time I repeat it for the equilibrium going down position, maybe I use a triangle here. This is now another new phase difference. Compared with respect to the pink colored cycle, this is half of a cycle. So it's half of 360, giving me 180 degree. Then finally, I pick another last set of points, say maybe this point here, the end of the cycle, oh, sorry. Which point do I wanted to pick already? This one, equilibrium going down, equilibrium going down. Okay, so let's just say right now I pick the next set of points to consider. On this wave here, let's just say I pick this one, the end of the cycle for the smaller wave. And then for the larger wave, I pick a similar point, which is again the end of the cycle. This is another phase difference. You see now this phase difference here, compared with respect to the smaller cycle, this one is actually 360 degrees phase difference. Okay, so you see when the waves do not have same period, they do not have same frequency, you will notice that when you pick the corresponding pair of points, the phase difference is always going to be different. You see the first set of points that you pick had a phase difference of 0. Then the second set of points you pick had a phase difference of 90. The third set of points that you pick had a phase difference of 180. Then the last set of points you pick had a phase difference of 360. Okay, so you see here, this is not coherence. Coherence is when you have constant phase difference. So you look at the previous 4 examples here. Just now, I analyzed this diagram here. You will notice that no matter which points I pick, the phase difference is always the same. Okay, it's always going to be 180 degrees. But you see this one here, if I choose a different set of points, my phase difference is always going to be 0. My phase difference is always going to be different. So this is not coherence. All right. So that's why here I mentioned this. Two waves with different frequencies will result in phase differences that are continuously varying. So the waves will never be coherent. Okay. All right. So when waves are coherent, you should understand by now that they must always have same period and same frequency. But how do you relate the same speed and same wavelength thing? Remember in your last chapter, I also mentioned that waves of the same type in the same medium will always have the same speed. Okay, so in the last chapter I also mentioned this, waves of the same type in the same medium will always have the same speed. So here we are assuming that the two waves that meet at a point here, they are obviously in the same medium because they're meeting at the same point. Okay, and for superposition, we mentioned that superposition can only happen when the waves are of the same type. Remember in page 2 of your notes, I mentioned that for superposition of an interference to occur, there are a few conditions to satisfy. They must meet at a point, they must be the same type of wave, and they must be polarized in the same direction. So here, the thing here is that when we're talking about comparing between two waves that meet at a point, they obviously, if they are interacting with each other to give you a new wave, they obviously must be the same type of wave. And then if they're meeting at a point, they must be the same, they must be in the same medium. So therefore, they must have same speed. Okay, so that's how I can conclude that coherent waves must have the same speed. Okay, so how do I then also conclude that they have the same wavelength? That one is based on V equals to F lambda. Okay, so you see, if coherence means that the frequency must be same and the speed must be same, obviously the wavelength would be same also. Okay, so they're all kind of interrelated. All right, but whether or not but you don't really need to worry about trying to explain this. In your exams, you won't be asked to explain why is it that coherent waves have same period, same frequency, same speed, same wavelength. No, you won't be required to explain this. You're only required to know that as long as the waves are coherent, these properties will always be the same. Period same, frequency same, speed same, wavelength same. Okay, that's the key take-off point here.